Chapter 5, Simulating Data. Section 5.1, Why Simulate Data? Why should you use simulated data when learning about statistics? Let us count the ways. Validate analysis methods. A vast array of data analysis methods exists, each with parameters that can influence the outcomes. By simulating data, you can compare the results of a statistical test with the known ground truth patterns embedded within the data. This benchmarking process allows you to evaluate the validity of analyses and is particularly useful when the simulated data have characteristics similar to those in real data. Understand advantages and limitations of analysis methods. Simulating data allows you to manipulate effect sizes and noise characteristics, which is not possible in real data. This gives you the tools to understand the boundary conditions where analysis methods no longer produce meaningful or accurate results. Understand how analysis methods work. To understand a statistical analysis, it is helpful to read explanations and look at equations, but supplementing this approach with simulated data provides a much deeper understanding. Understand your data better. One of the goals of simulating data is to create fake data sets that have similar characteristics as you would find in real data. Thus, the process of simulating data will help you analyze and interpret real data. Think more carefully and critically about data. The thing about modern software packages is that almost anyone can run an analysis by copying and pasting a few lines of code. If you want to transition from a novice to an expert data modeler, you need to develop a deep understanding of what to expect from data, how to treat data, how to select an appropriate analysis method, and how to visualize and interpret the results. Expert data analysts take a proactive view of understanding data, while novices take a reactive approach and basically just start throwing models against the data to see what sticks. So testing models using simulated data allows you to develop intuition for the kinds of statistical analyses that are likely to be successful on specific types of data and with certain kinds of distribution. Computational statistics. There is a family of statistical methods called computational statistics or empirical statistics that rely on simulating, sampling, or shuffling data to compute statistical significance. Such methods include bootstrapping, confidence intervals, permutation testing, and statistical power estimations. You will learn all of these methods in later chapters, but the point is that simulating data can be necessary when data violate assumptions that are required for parametric statistics. Improve thinking skills. Simulating data in a precise and appropriate manner requires critical thinking, strategic planning, adaptability, and creative innovation. Therefore, simulating data is an opportunity to develop your own ability to think critically and to see the big picture while also focusing on the details. Improve programming skills. Data are simulated using code, and so learning to simulate data will improve your coding skills. Convenience. Simulating data allows you to try out new statistical algorithms without needing to run experiments or spend hours searching for online datasets, only to find that they are poorly documented or require a considerable amount of reformatting and processing. Fun. If you've never simulated data before, then you're in for a treat. I think you will enjoy it. Please forgive me for reminding you of an important point about the ethics of making up data. Simulating data is great and completely ethical. Leading your audience to believe that fake data are real, either by stating that the data are real or by failing to explain that the data are fake, is unethical. Section 5.2, Random Data from Distributions. In the previous chapter, I introduced distributions as histograms created from data. The idea is that you start with a data set that has an unknown distribution, and the goal of creating a histogram is to discover that distribution using visual inspection and descriptive statistics. Simulating data turns this order around. Instead of starting with data, you start with a distribution. You can select the shape and the descriptive statistical characteristics, and then generate random data that conform to those characteristics. This provides a powerful way to understand and explore statistics, which is why I believe that learning how to simulate data should be a core aspect of statistical training. The purpose of this section is to show you how to generate random data from various distributions. All the concepts and formulas introduced here are implemented in the exercises at the end of this chapter. This paragraph references Figure 5.1. Figure 5.1 has two panels, Panel A on top and Panel B below. In Panel A, we see on the left a matrix of numbers 0 through 8 organized in a 3 by 3 grid, and an arrow pointing to a distribution. And in Panel B, we have the title Simulating Data. That shows a distribution, looks like an X-Gaussian distribution, so something like a Gaussian with a bit of a right skew. And that has an arrow next to it which points to a matrix of data. The concept illustrated in this figure is that in Panel A, analyzing real data involves determining the distribution of observed data, and in Panel B, creating simulated data involves generating random numbers based on desired distribution characteristics. Section 5.2.1, Normally Distributed Random Data. You are already familiar with the normal, also known as Gaussian, distribution of data. The math notation for data drawn from a normal distribution is shown in equation 5.1. This equation reads x tilde n, and then in parenthesis we have mu comma sigma squared n parenthesis. Now the n here is not a normal looking n. It is slightly italicized and a little bit baroque, so it has a little bit of a foot and a head to it. My description will make more sense when you are looking at the equation. So this equation states that data set X is drawn from a normal, that's what the n stands for, distribution with a population mean of mu and a population variance of sigma squared. Notice the tilde sign instead of an equal sign, and that tilde sign means is distributed as. Now, equation 5.1 doesn't tell you everything about the data set. For example, the number of data points, possible outliers, skew, kurtosis, etc., although you can assume that all moments are consistent with a theoretical normal distribution unless otherwise indicated. In some books or courses, you might see the distribution defined using the standard deviation, as in n mu comma sigma. That is less common though, so you can assume that the second parameter refers to variance, sigma squared. N 0, 1, that is when mu is 0 and sigma squared is 1, is referred to as the standard normal distribution. Figure 5.2 shows 4 examples of data sets comprising random numbers sampled from normal distributions with different parameters. I obtain these distributions by generating histograms from data generated using NumPy's random module, and you can also use R's functions for random numbers. The titles in the figures indicate the means and the variances that I specified, and the empirical means and variances that I computed from the random data sets. So figure 5.2 has 4 panels arranged in a 2 by 2 grid. They all show histograms that are roughly Gaussian looking, and what is noteworthy about these histograms is the titles on top. So for example, the top left panel has the title that spans 2 rows. The top row is mu equals -1. x bar equals minus 1.018. And the line underneath says sigma equals 1. Standard deviation of x equals 1.00. Back to the text. Why are the empirical descriptive statistics different from the parameters that I specified in the Python functions? This is due to sampling variability, which is the main reason why we need inferential statistics. You will be able to explore this discrepancy more in the exercises of this chapter, and I'll have a lot more to say about the issue in chapters 8 and 9. For now, suffice it to say that sampling variability implies that randomly sampled data characteristics won't exactly match the population characteristics you specify in the function parameters. As an extreme example, imagine you draw one number at random from a normal distribution with a mean of 0. That number might be, say, 0.42, and the average of that n equals 1 dataset is obviously not 0. Footnote: it is possible to make the empirical descriptive statistics exactly match the target statistics through normalization, and you'll learn how to do that in the next chapter. Stretching and shifting. When simulating data, I think about the mean and standard deviation parameters as shifting and stretching. These are not formal statistical terms, but I find them useful for understanding the impact of manipulating the first two statistical moments on the resulting distribution. The mean shifts the distribution left to right without changing its shape, while the standard deviation or the variance stretches or compresses the distribution without changing its center location. NumPy additionally refers to these as location, which I call shifting, and scaling, which I call stretching. I'm sure there are even more terms that people use. I suppose it would be ideal to have one consistent set of terms, but I highly doubt that a globally distributed group of statisticians will ever agree on anything. Indeed, friendly disagreements is an important driver of progress in science. Section 5.2.2, Uniformly Distributed Data. Data randomly drawn from a uniform distribution are described by the following mathematical expression. Equation 5.2 reads x tilde u, and the u is also kind of funny looking in the way that the n was funny looking in the previous section. So x tilde u parenthesis a comma b n parenthesis. Now, this may look really similar to equation 5.1 for the normal distribution, but the two parameters are not the mean and variance or any other statistical moment. Instead, a and b are the lower and upper bounds of that distribution. Common default parameters are a equals 0 and b equals 1. In other words, random numbers that are uniformly distributed between 0 and 1. So u 0, 1 is called the standard uniform distribution. Footnote: technically speaking, the distribution is defined on the half-open interval, bracket 0, 1, parenthesis, meaning that exactly 1 is excluded. In practice, however, rounding errors produce a distribution in the closed interval of 0, 1. This paragraph refers to figure 5.3. Figure 5.3 shows a plateau-shaped function, so it is 0 for values below x equals 0, and it is also 0 for x values above 1, and it has a common value above or between 0 and 1, and the y-axis is labeled probability. Back to the text. It turns out that any uniform distribution can be created by shifting and scaling a standard uniform distribution. For example, what are the upper and lower bounds of dataset y in the following equations? So in equation 5.3, we have x is distributed as uniform numbers between 0 and 1. And then equation 5.4, we have dataset y equals 2 pi x minus pi. And the question is, what are the upper and lower bounds of dataset Y? Now, the way to think about it is to replace the X of dataset X with its boundaries, 0 to 1, and then you just plug in. So in the above example, that gives 2 pi times, in square brackets, 0, 1 minus pi, equals 0, 2 pi in square brackets, minus pi, and that equals minus pi to plus pi. In other words, we've created a data set with random numbers drawn from a uniform distribution that could be used to simulate phase angles. Data with these characteristics are used in signal processing, computational geometry, and complex analysis. More generally, to create a uniform distribution with any arbitrary boundaries A and B, we assume that A is less than B, you start from a standard uniform distribution and apply the following formula. Equation 5.5 reads Y, so dataset Y equals A plus parenthesis B minus A and parenthesis U, where U is defined in equation 5.6 to be distributed as the uniform distribution with bounds 0, 1, so standard uniform distribution. Figure 5.4 shows a few examples. For uniform distributions, the empirical and specified boundaries are very likely to match more closely compared to the descriptive statistical characteristics specified when creating a normal distribution. Now, due to sampling variability in finite samples, the empirical boundaries might not exactly match the A and B parameters, but min-max scaling, a transformation algorithm that you'll learn about in the next chapter, can guarantee a perfect match. This paragraph references figure 5.4, which shows 4 panels of histograms similar to figure 5.2. In each of these 4 subpanels, we see a uniform histogram of uniformly distributed data, where again we have the A and B parameters that I defined when I created the data sets, and then we have the empirical min and max values of Y. These match very closely, though not necessarily always identically. For example, in the top left panel, we see that A, the parameter A, is minus 1, but the empirical minimum of Y is minus 0.999. So it's quite close. Back to the text. Equation 5.2 does not prescribe the mean or the variance of the data. So what do you do if you want to create a uniform distribution with a specified mean and variance? Let me start by defining the expected mean and variance of a uniform distribution given the boundaries A and B. So equation 5.7 states that mu, with the mean, equals A plus B divided by 2, so the average of A and B. Equation 5.8 states that sigma squared equals the ratio of the quantity A minus B squared divided by 12. I believe that equation 5.7 is intuitive without deeper explanation. If the numerical values occur with uniform probability between A and B, then we can expect the average of the data set to be the average of the boundaries. Equation 5.8 probably seems strange and arbitrary. Why is the difference of the boundaries squared, and why the division by 12? I promise I'm not evading the answer, but I don't want to take the time to explain it now. The reason is that these two formulas come directly from the definition of expected value and statistical moments. Expected value is a topic in probability theory, and so we will return to this issue with a full explanation and derivation of those formulas in Chapter 8. For now, suffice it to say that those formulas and the curious little factor of 12 are the result of applying the definition of expected variance and working through some calculus and some algebra. In exercise 2, you will empirically confirm that those formulas are correct. If you are comfortable with integral calculus and don't have the patience to wait until Chapter 8, you can skip forward to section 8.7. Now back to the question at hand. Let's say you want to create a data set with uniformly distributed numbers with a specified mean and standard deviation. Equation 5.9 has what you need. Equation 5.9 states that dataset y is equal to mu plus the square root of 3 times sigma times the quantity 2 times u minus 1, where u is distributed as uniform numbers between 0 and 1. In other words, u is distributed using the standard uniform distribution. I would like you to understand equation 5.9 intuitively before worrying about where it comes from. So the 2u minus 1 term stretches and shifts the uniform distribution to be centered around 0 with boundaries of minus 1 to plus 1. And then the multiplication by the square root of 3 sigma stretches that distribution to have boundaries of minus square root of 3 times sigma to plus square root of 3 times sigma. And then we shift that distribution again by mu. Now, there's no great mystery to equation 5.9. It can be derived by solving for a and b using equations 5.7 and 5.8. Here's a hint. Take the square root to have an expression for sigma instead of sigma squared. And then you just plug in those expressions into equation 5.5. Section 5.2.3, random data from other distributions. There are myriad distributions that you can draw random data from. I will present a couple of examples below, but the general point is that there are two ways to create data sets with a distribution other than normal or uniform. You can find a Python or R function that returns random numbers from your desired distribution, or you can start from a normal or uniform distribution and then apply some mathematical transformation. As an example of the first approach, we can create random data from a Weibull distribution. This is shown in figure 5.5, which I will describe in a moment, using the Python function numpy.random.weibull. I won't go into detail about the nature, definition, or the applications of a Weibull distribution because it's not used in this book. The point is just to illustrate using a Python function to generate random numbers from a particular distribution. In exercise 9, I will expand on this approach. So figure 5.5 shows a histogram of example random data drawn from a Weibull distribution using numpy.random.weibull. The histogram looks roughly Gaussian, although it's a little bit wider than a Gaussian. It is strictly positive and it is right skewed. Back to the text. The other approach is to pass normally or uniformly distributed numbers through some mathematical transformation. I already introduced the concept of uniformly distributed numbers in the range of minus pi to plus pi via stretching and shifting a standard uniform distribution. Another example, which you will recognize from the exercises in the previous chapter, is numbers randomly drawn from a log normal distribution. A log normal distribution is created by passing normally distributed numbers through the natural exponential function. Formally, it looks like this. We have equation 511 states that dataset y equals e to the quantity x times sigma plus mu, where x is random numbers drawn from a standard normal distribution. Figure 5.6 shows an example of a log normal distribution, and exercises 3 and 10 will give you hands-on training with creating and characterizing log normal data. Footnote: it is called log normal but defined as e to the x because the log of equation 5.11 is normally distributed. And I agree with you, it seems sensible to call this an exponential distribution. But that term actually corresponds to the function e to the minus lambda x for x is greater than or equal to 0. So the previous paragraph references figure 5.6, which shows a histogram of numbers randomly drawn from a log normal distribution. A log normal distribution looks roughly a little bit Gaussianish, but is right skewed. It falls precipitously to 0 on the left side of the peak, and it is strictly positive. Section 5.2.4, Random Integers. There are myriad applications of random integers ranging from algorithms to random events in video games to cryptography. In this book, we will often use random integers as indices to select from a data set and also to simulate labeled data. You can generate a data set of uniformly distributed integers in Python using NumPy's random.randint function. The function works similarly to generating uniform distributed data in that you specify lower and upper bounds and a sample size, and the function returns a data set with those parameters. The upper bound is exclusive, meaning that the code numpy.random.randint1, 5 will return an integer randomly selected from the set 1, 2, 3, 4. So the upper bound of 5 is excluded. This function will generate uniformly distributed integers. If you want an integer data set with some other distribution, you can generate non-integer data in some other distribution and then round the results to the nearest integer. More on this in exercise 7. In R, you use the sample function and input the integers from which to sample. For example, the code sample parenthesis 1:4, size equals 1 will return an integer randomly selected from the set 1, 2, 3, or 4. The sample function has a multitude of applications that you will discover throughout this chapter. Section 3.5, Random Elements of a Set. In this section, I will show you how to select data at random from an existing data set. For example, let's say you want to select one item at random from the set 1, 2, 3, 6, 7, 8. There are several applications of randomly selecting from a set, including creating surrogate data sets based on real data and permutation statistics, and bootstrapping. You will learn those techniques later in the book, but I want you to know that the methods you'll learn in this section have important applications in modern computational statistics. Let's start with random selections from a set. Consider the following Python code and guess a possible output of the second line. So there are 2 lines of Python code. Here, I'll get to the R code in a moment. The first line of the Python code defines a list of the elements 1, 2, pi, and 10 in variable s. The second line reads numpy.random.choice s, 1. The corresponding R code is also in 2 lines. The first line defines the variable s to be a collection of the numbers 1, 2, pi, and 10. The second line is sample s, 1. Back to the text. The first time I ran this code, it returned 2. Then I ran the same 2 lines of code again, and it returned 10. Run the code over and over again, and you'll get a result that is unpredictable, except that it will be one number from that list. It will return only one number because the second input specifies the number of elements to return. By the way, the Python function choice and the R function sample will randomly select elements from any collection, a list or a tuple or a vector, not only numbers. For example, the following code will return a randomly selected element from the list T. Here we see code that is very similar to the code I just described, except now the variable T instead of S is a list, or in R, a collection of the text A in double quotes, B in double quotes, and hello in double quotes. Back to the text. Let's return to the previous example with numbers. What would happen if we set the second input to 4? There are only 4 elements in the list, so you might expect the function to return all 4 elements, perhaps in a random order. Let's see what I got when I ran the code. Here we have one line of code and a line of output, The code reads numpy.random.choice s, 4, and the output on the following line is an array of the elements 10, 1, 1, 3.14, 159. Back to the text. What happened to the 2, and why did the 1 appear twice? There is a parameter of random sampling called replacement. Random sampling with replacement means that each item is put back into the list after it is selected, whereas random sampling without replacement means that once an item is selected, it's removed from the set. This distinction is illustrated in Figure 5.7. Figure 5.7 illustrates random sampling without, which is in panel A, I'll describe that in a moment, and with replacement in panel B, I'll describe that in a moment. So we see three sets of buckets, three pairs of buckets labeled sample 1, sample 2, sample 3. The idea, the concept being illustrated in the figure is that random objects are being pulled out of one bucket on the left and being placed into another bucket on the right. Now in panel A, we see sampling without replacement. So each time an object is removed from the left bucket and placed into the right bucket, that item is permanently gone from the left bucket. It disappears. It's no longer present in the left bucket. Panel B is titled Sampling with Replacement. And here we see that the bucket remains full each time you draw an element out of the left bucket and into the right bucket. This means that the left bucket can provide the same element multiple times in multiple samples. Back to the text. This is no trivial distinction. Sampling with replacement means you can create a new dataset that is larger than its parent dataset because some elements will be sampled multiple times. Footnote. What happens if you try to randomly sample k greater than n elements without replacement? Try it in code and find out. Back to the text. It also means that randomly sampling n values from an n element dataset can produce a new dataset with descriptive statistics that are different from those of the original dataset. You saw this in the example above when the number 1 was selected twice while the number 2 was not selected. Had we sampled without replacement, the new dataset would be identical to the original dataset, except that the order of the elements could differ. In fact, random sampling without replacement is a mechanism of random permutations, which you will learn about in the following section. Section 5.4, Random Permutations. Permuting, or shuffling, is a way of randomizing the order of elements in a list or array without modifying the values of those elements and without subsampling or oversampling like in the previous section. Here's a simple example in code. The Python code reads L equals numpy.arange5, and then we print L, and then we print numpy.random.permutation L. So the first output line is the numbers 0, 1, 2, 3, 4. The second output line corresponding to the output of numpy.random.permutation is 2, 0, 1, 3, 4. The R code is comparable, but the code is seq, S-E-Q, 0, 4, 1. One application of permutation is to randomly resort sequential data. For example, let's create a data set of the integers -3 to +3 cubed, and then randomly reorder the sequence. So the Python code reads the data equals numpy.arange -3, 4 to the power of 3. Next line is new idx, variable new idx equals numpy.random.permutation, the length of the data. And then the next line reads shuff data equals the data new idx. Then we print out all three of these variables, and we see that the variable the data is -27, -8, -1, 0, 1, 8, 27. Variable new idx is the integers 3, 4, 1, 6, 2, 0, 5. And variable shuff data is 0, 1, -8, 27, -1, -27, 8. And then we have the R version of the code. It is comparable. We define the three variables as the data is seq, S-E-Q, the function seq sequence, -3, 3 to the power of 3. Next line. New IDX is the function sample, and then the input is length, the data. And finally, the third line is shuff data is the data with the indices new IDX. Back to the text. The variable new IDX contains the integers 0 through 6 in Python or 1 to 7 in R, which are indices into the variable the data. Notice that the number -27 is the first element in the data, but the sixth element in shuff data. In the Python result corresponding to index 0. Make sure you understand the difference between the data values and the indices into the vectors. This is an important distinction because the permuted indices, which is variable new IDX, are not data, but they are used to create a surrogate data set. One application of permutations is to randomize paired data samples. For example, imagine a data set containing the heights and weights of 50 people. You would expect those two features to be correlated. Now imagine that you randomly permuted heights but not weights. Would you still expect those two variables to be strongly correlated? Of course not, because the mapping between heights and weights has been randomized. Therefore, computing correlations in shuffled data can be used to measure the correlation due to random chance. Exercise 8 will help you implement this, and Chapter 16 will explain why this is useful for inferential statistics. Section 5.5, Reproducing Randomness. Every time you call a randomization function, you'll get a different set of numbers. That makes sense, right? Of course. If the numbers were the same each time you called the function, then they wouldn't be random, right? Actually, there are good reasons to want reproducible randomness. For example, being able to reproduce an exact random sequence guarantees that someone can exactly replicate your findings. Let's start by showing that repeatedly generating random numbers leads to different results. If you have a Python or R session open, run the following code. Python, we have numpy.random.randn 3, 3, and in R, we have matrix R norm n equals 9, n rows equals 3, n col equals 3. So this code generates a 3 by 3 matrix of numbers randomly drawn from a normal distribution. Run the code several times and notice that the matrix of numbers is different each time, although the code hasn't changed. Now I'll try the following. In Python, we have two lines of code. rs equals numpy.random.randomState 17. And then the next line is rs.randn 3, 3. In R, we have the code set.seed 17. And then the following line is print matrix r norm n row equal 3, n col equal 3. And then we see the output of Python and the output of the R code that I described. Back to the text. I am quite sure that you will get exactly the same output that is printed above. And how do I know this? Because the Python function randomState and the R function set.seed initialize a seed for randomness. So all random numbers are in the same sequence. Footnote. The reason Python and R produce different random number sequences with the same seed is that each language implements its own pseudo-random number generator based on distinct algorithms or variations of those algorithms. Back to the text. For this reason, seeded random numbers are called pseudo-random numbers, or sometimes pseudo-random number sequences. Footnote. To be precise, no computer-generated numbers are truly random. They are the result of complex algorithms that produce numbers that seem random to us and that are difficult, though not impossible, to predict. Now, for our statistical purposes, a simple pseudo-random generator is sufficient. Applications like cryptography and gambling machines require more sophistication to achieve unpredictable randomness. Back to the text. The seed ensures the reproducibility of random numbers only when you utilize a random number generating function following the variable rs. Thus, calling numpy.random.randn will yield a new and unpredictable set of random numbers even after defining a random seed. The primary advantage of seeding random numbers is that it allows you to reproduce an exact result from any computer at any time. Had I seeded the random number generator every time I generated random numbers in this book, you would be able to reproduce every result and figure, not just qualitatively, but exactly numerically. So, shouldn't you always seed? You might think that seeding your random number generator is the best way to learn because, for example, you can exactly reproduce every single result and simulation in this book. There is a case to be made for that argument, and I am sympathetic to that motivation. However, I do not think that seeding the random number generator is a good way to learn statistics. One of the important lessons in statistics and empirical science more generally is that data samples contain multiple sources of variability and noise, and that repeating the same experiment can lead to different results. It is important to know how robust certain results or algorithms are to such variability. And so learning from one specific example is dangerous because a particular result might arise from a quirk in one random sample instead of reflecting a general principle. The same can be said of empirical sciences, which is why a large number of experiment replications and why large sample sizes are so crucial to progress in science. So for these reasons, I do not use random seeding, but seeding is important to know about, and of course you are free to disagree with my motivations to use random seeding in your education, your research, your applications, and your teaching. Section 5.6, Running Experiments with Random Numbers. One of the primary ways to use simulated data to understand statistical methods is to perform experiments. In this section, I will justify that claim and then explain how to run experiments using random data. Let's start with a basic question. What is the point of an experiment? You conduct an experiment when you want to understand something that you currently do not understand. Scientific experiments begin with a research question, which is then translated into an hypothesis, from which an experiment designed and then data are collected, and finally, the empirical data are processed and analyzed. Statistical experiments with simulated data are similar. You want to understand an analysis that you don't currently understand. So you begin with a research question. For example, how does standard deviation in one variable impact the correlation with another variable? That's an example of a research question. Then you design the experiment, for example, deciding how to vary the standard deviation and the correlation strength. And then you write code to implement the experiment and visualize the results. And then you analyze and interpret the findings to increase your knowledge of statistics. Importantly, the insights you can gain from statistical experiments with fake data exceed those insights that you can gain just by looking at equations or code. For example, you might wonder, what is the impact of inhomogeneity of variance on the statistical significance of an interaction term in an ANOVA? Quite a mouthful there. Sure, you can ask an experienced statistics professor, but the answer is probably going to be along the lines of, well, it's not ideal, but ANOVAs tend to be robust unless the variance differences are extreme. Now, staring at the equations for an ANOVA is unlikely to provide deep insights. And if you don't believe me, you can flip forward to chapter 14 and see if you can answer this question by looking at those equations. So, my recommendation is to design, code, and conduct an experiment in which you systematically manipulate the variance in one ANOVA cell while holding the variance in the other cells constant. This will give you an answer that you can visualize, understand, and explain to others. As I wrote at the outset of this chapter, experiments with fake random data are advantageous because you can control the data characteristics and apply manipulations in ways that are impossible in real experiments. The main disadvantage of fake data is that simulating characteristics of real data, that is, creating what I call a data pastiche, can be difficult or impossible. On the other hand, the goal of running experiments with simulated data, and certainly how you will use simulations in this book, is to understand statistical methods, not to replace empirical experiments. And there's a margin note here. Important point. Experiments with fake data allow you to learn about statistical methods. Experiments with real data allow you to use statistical methods to learn about the universe. Section 5.6.1 Experiment Impact of Standard Deviation on Mean. To make this concrete, let's run an experiment. The goal of this experiment is to determine the impact of the standard deviation on the estimate of the mean in normally distributed data. Here's the thing. In theory, the standard deviation has no impact on the mean because the standard deviation is defined as the dispersion around the mean. It does not bias the mean itself, at least not in a normal distribution. But theory does not always translate into practice, especially with smaller samples and noise. So we will run an experiment to help us understand the impact of standard deviation on the mean. The key question is about standard deviation, so that's the variable that we will manipulate. There are other variables that could be manipulated, including the expected average, sample size, distribution shape, and so on, but we'll keep these factors fixed in the interest of brevity and directness. Here's how it works. I created a dataset of 100 random numbers drawn from a normal distribution with an expected population mean of 0 and a standard deviation of 0.01. The empirical mean of that dataset was 0.0453. Not exactly 0, but close. Then I created another dataset with the same sample size and expected population mean, but with a standard deviation of 5. Now the empirical mean of that data was 0.6231, much further away from 0. Okay, so those were two individual random samples. Now the idea of an experiment is to repeat this process of data generation and analysis. Now in this case, the analysis is just to compute the mean. But you repeat this process multiple times, each time systematically varying the standard deviation. This was done in a for loop in code such that within each iteration of the for loop, I created a new dataset using the same expected average and sample size, but a different standard deviation. There were 40 standard deviation values that ranged from 0.01 to 10. And at each iteration, I computed the empirical mean and stored that value in a vector, and then plotted the resulting empirical averages as a function of the standard deviation. Now, before reading the text below, please take a moment to inspect Figure 5.8 and make some observations about the relationship between standard deviation and mean estimation. Figure 5.8 shows the results from my experiment. It is a scatter plot with the x-axis going from 0 up to 10, and the label of the x-axis is population standard deviation. The y-axis, it goes from around minus 1.5 to plus 1.5, and the label is empirical mean. And we see a horizontal dashed line at y equals 0. This is the theoretical population mean. And then we see a bunch of gray squares that are kind of scattered around, and those are the empirical means plotted as a function of the population standard deviation. And what you see when you look at this graph is that for small population standard deviation values close to 0 on the left of the plot, the empirical sample means tend to be fairly close to 0. And as the population standard deviation gets larger, going to the right, basically the dispersion gets bigger. So we see squares or empirical means that are further away from the horizontal line of y equals 0. Back to the text. Are you surprised by the results? All of the data were generated from a theoretical distribution with a mean of 0. So how is it possible that we got empirical averages as extreme as greater than 1 or less than -1? The discrepancies are due to sampling variability and random noise. This is a serious issue in real data and one of the primary reasons why we need inferential statistics. Two other observations. First, the empirical means get further away from 0 with increasing standard deviation. Now, that should feel like an intuitive result, but, intuition is not always correct in mathematics or in the rest of life, really. Second observation, the empirical means are both above and below the expected mean, suggesting that standard deviation introduces a non-systematic bias. And this can be contrasted with a systematic bias that would shift the empirical mean in one direction. This can happen, for example, with a log normal distribution, as you will discover in exercise 10. Now, I found the results of this experiment curious, so I designed a follow-up experiment to determine the impact of sample size on the relationship between standard deviation and the estimate of the mean. So to run this experiment, I modified the code to create two data sets, one with a sample size of 100 and one with a sample size of 10,000 without changing any of the other parameters. And the results are shown in figure 5.9. And what are your observations? So figure 5.9 looks very similar to figure 5.8 that I have recently described. Difference is that here we have light gray squares corresponding to the experiments run with n equals 100, so sample size of 100. And then we have dark gray circles plotted also on this scatter plot. And the dark gray circles correspond to sample sizes of n equals 10,000. And then what you see is that the circles are much, much closer to the horizontal dashed line at y equals 0 compared to the light gray squares, which are much further away from the y equals 0 line. Back to the text. A myriad of possible experiments. A moment's consideration will reveal how sophisticated even this small experiment can become. You could additionally systematically vary the expected mean, the sample size, that is, more sample sizes spanning a broader range. You could systematically vary the data distribution, like normal or uniform or log normal or power law, and so on. You could change the quantification, for example, by computing the distance of the empirical mean to the expected population mean. Now, here I made only qualitative interpretations of the results. We could apply statistical analyses to quantify the outcomes and compare those outcomes across, for example, different data distributions. We could repeat this entire experiment multiple times to quantify the amount of variability of the empirical means for each standard deviation value. And these are just some of the ideas that I had while writing this paragraph. Perhaps you have additional ideas on how to expand this experiment. All that said, please try to keep your experiments simple and focused. The more complicated the experiment, the more difficult it is to interpret. This is true both for simulated experiments and for real-world experiments. The main purpose of this section is to introduce you to the idea of running experiments and simulated data by systematically manipulating one factor while keeping other factors constant. Okay, I hope you found this section useful. I attribute a lot of my understanding of statistics to running experiments with data simulation, and I hope your experience is similar. Section 5.7, the amazing world of data simulations. There are many more ways to simulate data than what I presented in this chapter. For example, researchers simulate time series signals, financial data, climate and weather patterns, images, biological and physical processes, traffic flows. The list goes on and on and on and on. Generative deep learning models are making impressive and sometimes terrifying strides in generating fake data, such as photographs of people who don't exist and deepfake videos that purportedly show famous people doing and saying things that they neither did nor said. The methods presented in this chapter are sufficient for this book, although I will introduce a few more data generation methods in later chapters. Other data generation techniques tend to be topic-specific, so you would learn about how to simulate climate data in a computational climate science course. The good news is that nearly all data generation methods are based on principles that you learned in this chapter, including drawing numbers randomly from some distribution, stretching and shifting, applying nonlinear transformations, and randomly permuting existing data. Section 5.8, finding publicly available real data sets. There is an ever-increasing amount of publicly available data that you can use for education, research, and commercial purposes. But there is no such thing as, quote, the data, end quote. There are countless data sets available online with varying characteristics, sample sizes, and quality. Similarly, there is no single repository for all available data. Indeed, many data repositories are discipline-specific. This means that to find a particular type of dataset, you first decide the kind of data that you want, and then you search the internet for relevant keywords. Some data repositories are free and open, meaning you can simply click a link and download the data immediately. Other repositories are free, but require registration and some personal information. Some data are posted on personal websites or code repositories like GitHub. Some data sets are available by personal request to the author of a research report, but are not posted online. There are no universal standards for making data available or for the data format. If you want to get data online, you will need some patience and some persistence. I will mention here two specific popular websites for getting data: the UCI, University of California, Irvine Machine Learning Repository, and Kaggle, that is spelled Kaggle, Kaggle. I'll use several data sets from the UCI repository throughout this book. Please just be aware that, just because you can download data doesn't mean it's useful. Many data sets are, unfortunately and frustratingly, incomplete, poorly documented, or corrupted. This is not how it should be, but this is the reality, and you should be prepared for it. The good news is that more popular repositories are more likely to have higher quality, usable data. So although this book is focused on simulating data, I do have many exercises and examples with real data. They typically are the final exercises in each chapter. Section 5.9, Exercises. As I have mentioned at the end of previous audio chapters, I am not going to read the exercises here in this audiobook because I discussed them all in my YouTube channel. End of chapter 5.